the space that you kind of touched on, that's full of theories and is perhaps detached from appreciation of empirical evidence, or longing for empirical evidence, or grounding in empirical evidence, is the theoretical physics community and the interest in unifying the laws of physics and with the theory of everything. I'm not sure from which direction to approach this question, but how far away are we from arriving at a theory of everything, do you think? And how important is it to try to arrive at it, at this kind of goal of this beautiful, simple theory that unlocks the very, fundamental basis of our nature as we know it? And, and what are the kinds of approaches we need to take to get there?
Yeah, so in physics, the biggest challenge is to unify quantum mechanics with gravity.
Mm-hmm.
And I believe that once we have experimental evidence for how this happens in nature, in systems that have quantum mechanical effects, but also gravity is important, then the theory will fall into our lap, okay? But the mistake that is made by the community right now is to come up with the right theory from scratch. Einstein gave the illusion that you can just sit in your office and understand nature, when he came up with his general theory of relativity. But, first of all, perhaps he was lucky, but it's not a rule. The rule is that you need evidence to guide you, especially when dealing with quantum mechanics, which is really not intuitive. And so there are two places where the two theories meet. One is black holes, and there is a puzzle there. It's called the information paradox. In principle, you can throw the Encyclopedia Britannica into a black hole. It's a lot of information, and then it will be gone, because a black hole carries only three properties or qualities: the mass, the charge, and the spin, according to Einstein. But then when Hawking tried to bring in quantum mechanics to the game, he realized that black holes have a temperature and they radiate. This is called Hawking radiation. And it was sort of anticipated by Jacob Bekenstein before him, and Hawking wanted to prove Bekenstein wrong and then figure this out. And so what it means is black holes eventually evaporate. And they evaporate into radiation that doesn't carry this information, according to Hawking's calculation. And then the question is, according to quantum mechanics, information must be preserved. So where did the information go if a black hole is gone? And where is the information that was encoded in the encyclopedia when it went into the black hole? And to that question, we don't have an answer yet. It's one of those puzzles about black holes, and it touches on the interplay between quantum mechanics and gravity.